Good morning. My name is Katashi Nagao. Today, I'd like to talk about kind of virtual reality system. We call it building scale VR. That consists of the automatically created three-dimensional map of real building inside of real buildings, and its application to simulation of disaster situations. The whole buildings can be virtualized, and then we can move inside that building virtually, and then we can have an experience about disaster situation that it's difficult to realize in real space. So VR system has many applications in the near future. Latest hot issue of virtual reality is room scale. Have you ever heard room scale? So it's a new device like this kind device. We can move inside the room freely, walk around and touch something virtually. It's a room scale VR. So this case, the virtual reality space is limited inside single room. But we propose a new concept of virtual reality. It's called building scale. In that case, VR play area, that tracking area of headset and a controller is inside the whole building, like this. You know that if this is a virtual reality space, then people can move around inside the building like this, then experience the building virtually, but it's the same as a real building. That is called building scale. About data circulation in this server space, cyber and real space is called cyber physical system. So our research is related to cyber physical systems. So our research first create the three-dimensional world of real world. So this is a real building, and making a VR space based on this real space like this. So this is a virtual reality space. Then we can manipulate and that reconstruct inside the building, and change the layout, and place some special object inside the building in the virtual reality space. Then we can anticipate the future. We can recreate the future. Then so capturing the real world, then we can know current status of real world. And then manipulating the virtual space to anticipate the future. So this is like a data circulation, like this, capturing the real world and manipulating virtual world and feedback to the real world. If the building layout is not suitable for the, in the case of disaster situation, evacuation route and something. If the layout is not good, then change, then reconstruct the real space, and then capturing again to make a real to capture the real world and the virtual world, and making this kind of feedback loops. So this is another kind of data circulation. So that simulation in the virtual world, and reflecting in the real world, then make a real world data circulation. So about the history of this research. First, we developed a room scanning robot that is automatically creating a three-dimensional map. So that is an autonomous mobile robot to create the indoor 3D maps. It has 2D LiDAR, LiDAR means, laser, なんだっけthat to calculate the distance to the object in the 360 degrees, then scanning, then create the virtual world. This case 2D, it's not three-dimensional, but this robot also has a three-dimensional sensor. It's called RGBD camera. This case, Microsoft Kinect sensor. RGBD means RGB and depth. Depth is also the distance from camera to the object. It's a common technology to create a 2D map like this. 2D map. It's that very basic technology to create a map and estimate the current position of a robot, current direction and position of robot. It is a very common technology. So I think you have already studied about this kind of technology. No? 違う. It is called SLAM. Simultaneous localization and mapping. Have you ever heard that term? No? Okay. Have you ever heard ROS? No? Robot operating system. It's a basic function though. The ROS has this kind, SLAM technique already implemented. So you can easily use this kind of technology using a ROS. About process of indoor self-driving. So it is a little bit different from the indoor and outdoor driving. Outdoor driving is currently it's a very hot issue for the self-driving cars. But in this case, it's an indoor self-driving. First, as I mentioned, that a mobile robot, as I mentioned before, this kind of robot, create environmental maps by traveling inside the building, entire area of building. But this is just calculating the logs, moving around and sensing and accumulating the data. But it's a very noisy. There are many errors. So using the SLAM technology, it's possible to create a more accurate map like this. So calculating data, accumulating data, and removing the noise, and collecting the data, and then adding. Then create this kind of map, 2D map. Then robot or vehicle estimate the current position by comparing the sensor data and the map data. So that the robot can calculate sensing the distance from object, then matching the map. Then robot can estimate where it is now and which direction they are facing. So this is the demonstration of position detection. So this is the vehicle running inside the building, and this is the current position. Some noise occurs, turning, but it's adjusted by using the particle filters. Particle filter is a kind, probabilistic method to adjust the position of a robot. Then, so user specify the destination of robot. This here, ちょっと調子悪いですね。So here is here. あれ。ちょっと待ってね。Here is the current position, and here is destination. So then the system should make a route, optimal route from current position to the destination. To do that, we created this kind of mesh structure, that graph structure. So these blue lines and dots consist of a graph structure. It's a possible route move inside the building. Then this area has some obstacles. Then the robot cannot move, inside this area. Then lines are not, placed in this area. But then connecting the dots, nodes of the graph, then calculate the distance from the current position to the destination. Then the vehicle, robot, can decide which route is optimal. I mean that the shortest distance. Okay. So doing this kind of process, the robot can move around inside the building, very easily. So this is a demonstration of creating three-dimensional map inside the building. The building, I think this building. This building, the IB North, the first floor, the elevator area. Then the robot moving around the corridor of inside the building, then sensing the three-dimensional data by using RGBD camera, depths and the colors, and then adding vividity, then create this kind of three-dimensional data, and then estimating the plane, just before that, it's just a point cloud, but it's difficult to manipulate point cloud. So then create a planar space. Then create this kind of very noisy, but still noisy, because it depends on the accuracy of sensor. So now we have a more accurate sensor, three-dimensional sensor, so we can create a more cleaner going 3D map. Okay. So this is the process of automatic generation of three-dimensional map into a three-dimensional map. So first, robot create a route on which the robot operates when collecting the data of three-dimensional data from 2D map. 2D map created by SLAM technology. And then, running through the inside the building and accumulating the three-dimensional data by using RGBD camera. Then superimposing the such collected data. Then create the three-dimensional map. After that, polygonize, create the polygons based on the 3D point clouds. Then generate a 3D map that polygonized surfaces. Is that okay? Okay. That's as I mentioned, that it's an old version of our robots, 2012. Then currently we have a new robot. It is called room scanning robot. Like it's the same as the older one. Using the Roomba. Roomba is a cleaning robot. The mechanism is the same as the older one. Using Roomba. Actually, it is called Create. Create 2. It's a Roomba technology applied to education and research. So this cannot have cleaning functions. It's just a moving robot. But we have interface with this robot based on the loss, so we can easily control the Roomba moving. Also, we have two-dimensional LiDAR, but it's a little bit, precise, more finer resolution than the older one. And this is a new function. The older version just using the web camera, USB camera. But this version has panoramic camera, just three-dimensional and spatial, all-around panoramic image can be captured by using this camera. And the Kinect, Microsoft Kinect has been updated. So this is a new version. But currently, it's not sold. It's not being sold. It's out of order. The Microsoft stopped to develop the Kinect. So this latest, but the last version of Kinect. I'm very sad. Anyway, we're using these technologies, and devices to make this kind of robot. So as I mentioned, the robot based on the Roomba and has a new version of Kinect and three-dimensional, 360-degree camera on the top. So this is also the demonstration that the robot moving and creating the 3D map. In this case, the robot creates a point cloud 3D map, not polygonized. The robot automatically moving around inside the building, like this room. Yeah, automatically turning, and turning around and adjusting the direction and moving automatically. So this is the image captured by 360-degree camera. Ambient noise included, but we can clean up this noise because the image processing technology can remove outliers. You're moving faster than have a noise. Hmm. ちょっと難しいねこれね。But this video, we making a smaller resolution. So real data is more finer resolution. So this is 3D point cloud data. That is not clear, but the point cloud. So all data are points, colored points. So not object data, not surface data, just the points. But yeah, looks like object. So this is a three-dimensional map created by a new version of our robot. In the case of the desk, table, and the chairs, and such a movable object, then creating 3D data in different way. We call this kind of movable object is called operation targets. That means we can change the location by using controller or VR controller. So turn around the object, then then create this kind three-dimensional object. That case, we can move to change the position by using a VR controller. Because point clouds cannot be moved. Point clouds are not object. So we have to segment the point cloud into the more finer areas, finer space. So in this case, we can specify this is object, this is not object, like that. So then we specify to robot, so to scan this table or this whiteboard and so on. Then the robot moving around the object and create this kind of data. This is VR gear. As I showed, so current VR system is based on the room scale technology. So we can moving around and wearing this VR gear. We cannot see you. So anyway, so this is current technology. We can moving around VR space by using this kind of device. The VR headset and 3D sensor. As I talk later, we use a three-dimensional sensor, together with headset. This headset doesn't have any 3D sensor, but we add additional sensor to here. I talk it later. And backpack PC and the controller. This case, we are tracking knees, the legs. So then we attach the new sensor here. knee trackers. Anyway, then we tried to extend the tracking area because current VR system is just room scale. It's limited inside the room. But as I mentioned, we extend it to the building scale. Walking around, outside the door, and walking corridor. Also, we have to tracking the headset and hand. So we also developed additional technology to extend the tracking areas. But currently, another technology called inside out. But this case, VR system has this base station like that. Black cube. That, this one. This is a base station. This sensor to tracking the moving of this headset. But this limited, in like this area. So this is called outside-in tracking system. That requires sensors and transmitters. It's mounted on the ceiling, the facilities. But this technology is very good because accuracy is very good. Tracking accuracy, position accuracy is very good. But tracking area is limited. So another technology is called inside out. That headset has a sensor and no outside sensor and tracking itself. That is called inside out tracking. But it works, outside, without that kind of outside sensor. But accuracy is not good. So we can, feel bad, but tracking is not good. So moving and then walking, then have a headache, feel bad. So we improve that kind of situation based on the deep learning approach. So as I mentioned, we mounted, we attached a new sensor like this. This is a three-dimensional sensor. And we also developed a new deep learning method. So based on outside-in technology, based on this external sensor, but extending area, that's our technology. So this input is 3 RGB data, three-dimensional data. And the output is a 3D pose, position and orientation. So like this kind deep learning network, however hard convolutional neural network, it's a very basic deep learning technology. So the data is 299 times 299 image, and then depth data. And then that convolutional layer and Inception V3 that is developed by Google based on the ImageNet technology, and the gap and the dense layer. Then create a 3D position and 3D orientation. That's the input to Stream VR. Stream VR is like this the VR technology that making this headset tracking accurately. So our neural network replaces the data from the base station. So without base station, we can tracking the headset. In the case of controller, we are using this kind of marker, adding a marker to the controller, then using the camera. Then it's easy to detect the position of controller. So like AR, augmented reality technology. So adding a marker and scanning it by camera, then the marker, the position, and orientation can be detected very easily. As I mentioned, we developed a deep learning method to tracking controller and others. And headset and the controller and the knee tracker, then so we can extend tracking area whole inside the building. Okay. Another topic is multi-user, and this case, each user has each own the VR system, but connecting by network and transmitting that position and orientation data to another user. Then share the position of each user. And communication server is based on Photon server. It's developed by a third party. And based on Photon, it's easy to transfer the data between the user, VR users. And we then create the user shape like avatar, this kind of robot, like this. So by using the headset and controller and the knee tracker, and it's easy to tracking motion of user. So real space and the virtual space, almost same pose they can create. A little bit unnatural, almost okay. Now this is multi-user version.ちょっとわざとらしい。it's okay. Then we move on to the simulation like this, then simulate that, disaster situation like this. You have a very heavy situation. Well, maybe we cannot survive. But it's very serious situation. So it's very important to have an experience of this kind of situation. So it's easy to simulate the change in indoor situation during the disaster, like a fire situation, and water flood and earthquake and so on. So based on the VR space, it's easy to create this kind of situation. Then add and some visual and auditory effect, but smells and perfumes cannot be created, this time. But in the near future, it's very smelly, and so on. It can be created in the near future, but currently we cannot do that. And each object can move because it's a target, operation target. As I mentioned, that it's not point cloud, and it can movable and deformable. It's based on the move according to the law of physics. So anyway, the study of situation simulation method. Then in the near future involving the deformation, transfer the shape of objects. Yeah. Then ceiling breaking, and the wall breaks, and then the desk change deforms. It can be realized. So this is a multi-user situation.これは、いや、これは面白い。It's very interesting. ないよね、こういうことね。Yeah, it's difficult to compare that this virtual scene with a real situation because we cannot make a fire in this room, but so but we can feel it's real. It's not virtual. So that's very important. So based on this technology, evacuation drill can be executed. So very real situation, but virtual, accident. But we can experience such situation. That's a good experience. That we can react in the case of real disaster situation. This last topic. We also do some study based on the psychophysiological, like a brainwave. So EEG, brainwave data are used to compare human mental state in virtual and real experience. So like a working room, virtually and real, and compare the brainwave data. If the data are not so much different, then the virtual space is a good example for experience real. So this is a very simple version of EEG sensor. It's called NeuroSky, MindWave Mobile. And it can sense data, alpha wave, beta wave, gamma wave, delta wave, theta wave, like this. The alpha wave, beta wave, gamma wave, theta wave, delta wave. It's segmented, based on the frequency. And each brainwave has a very specific functions. Then we can estimate the mental state based on the brainwave. And this is the result. This alpha wave data, this is the beta wave data. It's difficult to mention that each situations are almost same, but not so much different. So this is a preliminary study. So we cannot say very we cannot conclude that VR space and real space are almost same. But this case not so different. So in the case of mental state, that VR space and real space, the users feel not so much different. But in the disaster situation, as you know, it's difficult to create disaster situation in real world. So we cannot compare the mental state between these situations. But this is the very safe experiment. Just walking and moving and communicating with other people. But brainwaves data are not so different. Anyway, we can conclude. Let me conclude this presentation. We developed breathing scale VR system that consists of indoor 3D point cloud map with operation targets that are based on the three-dimensional models created by automatically. And VR gears, headset, and backpack PC and so on are trackable in a full in-building space. So we call it a building scale VR. So based on building scale VR system, we developed a disaster simulation system. So disaster situation can be represented in a VR environment. And multi-user VR simulation can be performed based on our technology. It's useful for effective training of behavior in disaster situation, such as evacuation drill. And finally, I did some psychophysiological studies. That study suggested not a good result, but a very preliminary result that training in the virtual world is almost as effective as the real world. The most very similar situation. Few similar. And we have future work that include large-scale experiments with indoor 3D map with more complicated buildings. So we accumulated the data of the library, so this university library, and Toyota Auditorium. We created the 3D map of these buildings. So we can make more serious experiments based on such a 3D map. So if you are interested in this kind of research, so we can show you some demonstration, later, someday, not today. Okay, thank you very much. Any questions?大体いいですかね、これで。大体いいですか。はい、日本語でもいいよ、日本語でも。あ、はいはい。
じゃあ日本語いいですか。
いいよいいよ。
現段階では炎はランダムに発生させてる。
これはプログラムで発生させてるんで、ここから火を出そうみたいなことを制御してる。
あ、じゃあこの部屋の形に応じて。
そう。だからここは火が出やすいよねとか、例えばこの辺でなんかね、ヒーター使ってたらこの辺から火出やすいよねって言ったらエアコンから煙出やすいよねとか、そういうの全部制御できる。ただ火の燃え広がり方なんかをシミュレーションするのはなかなか難しいよね。だから材質とかね、木とかそういう材質を考慮しないといけない。そこまではまだできない。
結局、
はいはい、
災害の VR のやつはどうやって最終的に評価をしました。
おー、いい質問だね。Good question まだ評価っていう段階じゃないね。だからその人間の心理的な差を見るっていうのが一つのやり方だけど、本当の差じゃないからね。本当の災害じゃないからね。だから要するにリアルに感じましたかみたいな話だから、これは被験者実験しかできない。だからシステムの完成度はいかに自由度のあるシステムを作れるか、いかに簡単にその災害状況を再現できるかで、しかも専門家が見てこれは確かにこういう状況あり得るよねって判断できるか、それはできるよね。あとは被験者実験をしてどういうふうに感じましたか、これをあなたは経験として生かせますかみたいな。本当に生かせるかどうかはだってその状況が起こってみないと分からないから 実験は相当難しいよ。だけどこの注意にはなる。だからこういう時気をつけようみたいな、ね、だからこれはある意味未来の話だから、未来こういうことが起こったらこう対処しましょうねって話だから、本当の評価はできないけど、それが効果があるかぐらいはなんとか計測できる。だからそれで評価する。はい、いいですかね。Enough はい、Thank you very much はい、終わります。